So first of all, I would like to thank Hoju for his kind invitation. And I'm going to talk about the higher order Wirtinger inequalities, the relation with isoperimetric deficit, and some Minkowski-type inequalities. So this is our university, Kwok-Kun Kwong. So this is based on joint work with Hoju, and the title of our paper is this one here, and you can find on arXiv. So the talk is divided into two parts. The first part is some classical materials. So I will talk about the Wirtinger inequalities and the isoperimetric inequality on the plane. And the second part I'll discuss is generalization to higher dimensions and relation with the Minkowski inequalities. So if time permits, I will also mention some inequalities involving the mixed volumes. So the first part is about the classical case. So let's recall the isoperimetric inequality. So let's say we have a curve, simple closed curve on the plane. So something like this. And then let's say the length of the curve is L and the area is A. Then the classical isoperimetric inequality says that the square of the length is at least 4 pi times the area. And the equality case holds if and only if C is a circle. So of course, it tells you that for a fixed length, the largest area that it can enclose is exactly the area enclosed by the circle of the same length. So this is of course very classical, and there are many proofs and with many different generalizations to different spaces and different dimensions. So in today's talk, I'm going to discuss Hurwitz's proof of Fourier series. So basically our work is a generalization of the proof of Hurwitz, and actually he gave two proofs. So one is for general curves on the plane, and the other one is for convex curves. So it's interesting to see that the one which he wrote later is for a more special class of curves. However, this proof can be easily generalized to higher dimensions, whereas as far as I know, the first proof seems to work only for the two-dimensional case. So I'll mainly focus on the first proof, that means for the convex curves. In any case, for both proofs, a key ingredient is an analytic inequality called the Wirtinger's inequality. So it says that if we have a smooth function, which is 2 pi periodic, so in this talk, I'm not going to give the most general version of the inequality, so let's assume the function f to be as smooth as possible. And suppose the function f has mean 0, so integrate from 0 to 2 pi, the integral is 0. Then the Wirtinger's inequality tells you that the L2 norm of f prime is greater than or equal to the L2 norm of f. So that's the Wirtinger inequality, and actually you can easily characterize the equality case, and it holds if and only if f is a linear combination of cosine and sine. So our aim is to generalize the Wirtinger inequalities to higher order. So what I mean here is that you can regard this inequality as a first order inequality because it involves the first derivative. So for higher order case, we want to obtain some inequalities which involves second or third or any higher order of the function f, and it needs to be sharp. And if we can obtain such higher order Wirtinger's inequalities, then we want to obtain some higher order form of the isoperimetric inequality. So it turns out we'll apply our inequality to the so-called support function, which is basically some distance. So as you can expect, the integral of the derivative of that function will give you the length, and roughly speaking, the integral of the square of that function will give you the area. So if it involves higher order derivatives, so we'll expect that the higher order inequalities involve curvatures and also the higher derivatives of the curvature and so on. So let's look at the classical case. So what's the idea behind the Wirtinger's inequalities? So suppose now we have a 2 pi periodic function with mean 0. It's more convenient to use the complex notation. So using simple Fourier analysis, f can be expressed as Fourier expansion. So this is a linear combination of exponential int, and the assumption that f has mean 0 is equivalent to saying that the coefficient here, when n is 0, it is 0. So in other words, the combination here consists of only non-zero terms where n is non-zero. Here I ignore the issue of convergence and also smoothness. So let's assume f can be expressed as such kind of expansion. So in general, it may only be equal in some weaker sense, so in L2 sense. So in this case, if we differentiate f and ignoring the problem of convergence, then we just differentiate term by term. So we'll pull out in here. So f prime has such an expansion. And as is well known in Fourier analysis, so the L2 norm of f prime can be expressed using the Parseval's identity, which is the infinite dimensional Pythagoras theorem. And because there's an n here, so we can basically regard this exponential int as an orthonormal basis. So if we take the norm square of f prime, then we'll have n squared times the modulus squared of an. And because now n is non-zero, so n squared must be greater than or equal to 1. So if we replace by 1, then this is greater than or equal to the summation of modulus an squared. And that's exactly the L2 norm of f by the Parseval identities again. So this is very simple. The only inequality we have used is that n squared is greater than 1 if n is greater than 1. Okay, so this is rather simple. Now if we have the Wirtinger's inequality, so how can it be used to prove the isoperimetric inequality? So here comes the idea of Hurwitz. So let's assume that the curve is as smooth as possible and is convex. So you can regard convex as the condition that the curvature is always positive, or the domain bounded by it is a convex region. So first of all, it turns out it's best to make use of the so-called support function. So what it means is the following. So suppose this is our convex curve, and by convexity, so this curve can be parametrized by the inverse Gauss map. So in other words, the Gauss map is 1-to-1. So for each point here, we have a normal vector n, which is cosine theta sine theta, where theta is the normal angle here. And this turns out to be a parametrization due to convexity. So that means theta becomes a parameter of the curve. So the curve can now be parameterized by the inverse Gauss map x theta, where x is just the position. Then the support function is nothing but just the dot product of x with the normal vector at the point x. So in other words, so you look at the direction parallel to the normal direction, and then you just look at the projection of the position vector. So now this is the support function, and if you differentiate the support function, and because if you differentiate x, you obtain a tangent vector which is orthogonal to the normal vector. So if you differentiate, you get x dot with the derivative of n, and because you can easily see n and n prime forms an orthonormal basis, so x can be obtained by this linear combination of n and n prime, and because the dot product of x and n prime is just h prime, so x can be expressed in terms of n and n prime like this. So now we want to compute ds in terms of the theta. So you just compute the norm of the derivative of x with respect to theta. So using product rule, so you have such an expansion, and you can easily see that for the term h prime times n double prime is nothing but just negative n. Okay, so it will cancel with the first term here. So in the end, ds d theta is just the length of h plus h double prime. And on the other hand, we know that the curvature is expressed as d theta ds, so we take the reciprocal, and because of convexity, we can just assume that this term here is positive. So that means curvature is the reciprocal of h plus h double prime. So now we want to express everything in terms of the function h, the support function. So first of all, the length is easy, so we just make use of the change of variable formula. So because the Jacobian is h plus h double prime, so we integrate h plus h double prime, and by integration by parts, we can just ignore this term here. So the end result is that the length is just the integral of h. Okay, and on the other hand, we want to express the area in terms of h. So now we make use of the divergence theorem. So observe that the divergence of the position vector is 2. So if you use the divergence theorem, the area is just 1/2 of the integral of the divergence of x on the domain omega. So we use divergence theorem, we integrate x dot n on the boundary, and by definition, this is integrating h on the boundary. And now we want to convert this as an integral on a circle. So we plug in the Jacobian, which is h plus h double prime, and using integration by parts, that will become x squared minus h prime squared. So we want to convert it into this form here because we want to make use of the Wirtinger's inequality, which is of first order. So basically, it remains to show there's a relation between this integral here with this integral here. So it's natural to make use of the Wirtinger's inequality. So now, let's look at the proof of the isoperimetric inequality if we have the Wirtinger's inequality. So it's quite trivial once we have the Wirtinger's inequality, basically a two lines proof. So now the Wirtinger's inequality tells you that if a function has mean 0, then its L2 norm is bounded by the L2 norm of its derivative. So now if we subtract the mean from the support function h and take the L2 norm, it's bounded by the L2 norm of its derivative. So we are arranging so we can obtain this inequality, and we arrange this way because the left hand side is nothing but just the area, but the right hand side is nothing but just the square of the length. So that's exactly the isoperimetric inequality. And of course, by looking at the equality case of the Wirtinger's inequality, so the Wirtinger's inequality is proved by the Fourier analysis, and the only inequality in the proof is the fact that n squared is greater than or equal to 1. So of course, if the equality holds, then for any coefficients where n is greater than or equal to 2, they have to vanish, so only the linear term is left. So that means h has to be a linear combination of cosine sine, and from this it's easy to see that the equality case is obtained if and only if it's a circle. So now we want to generalize it to higher order forms. So what we want to do is obtain sharp inequalities of the form some linear combination of the L2 norm of the higher derivatives of f. So of course here the coefficients CMK here are not always positive, otherwise this is just trivial. So now the key of Wirtinger's inequality is that basically n squared is greater than or equal to 1 whenever n is not 0. And the n here comes from the fact that if we differentiate f, we'll pull out the n here. So now in general, so you can regard this as equal. So if f has such an expansion, such a Fourier expansion, then by particles the L2 norm of the kth derivative is basically just n to the power 2k times the square of the modulus, and then take the sum. So let's say if we want to look for the second order Wirtinger's inequality, so that means we want to look for an inequality relating the summation of n to the power 4 times an squared, and also summation of n squared an squared, and the summation of an squared. So an easy observation is that we can make use of the same trick. So instead of using n squared minus 1 is greater than or equal to 0, so we replace it by this trivial algebraic inequality. So the product of n squared minus 1 squared and n squared minus 2 squared is always non-negative. So with this observation in mind, the thing that we have to do is just re-express this one in terms of the L2 norm of the derivatives of f, and that's quite easy. So you expand this one, so you obtain n to the power 4 plus 5n squared plus 4, and then multiply an squared to it. So we have such a combination, and then the first term here is nothing but just the L2 norm of f double prime. The second term, L2 norm of f prime. Third term is L2 norm of f. So we have obtained a sharp inequality involving the second derivative of f, and together with the first and zeroth derivative. Of course, provided that the function f has mean 0. So it should be clear that we can generalize this proof, and so we can prove the result that we have a general inequality like this. So it consists of all the derivative of f up to order m, and these coefficients here depends on both m and k. So it turns out the coefficients are the coefficients of the polynomial, the product of x minus j squared. So this should be quite clear from the proof. So we have n squared minus 1 squared, n squared minus 2 squared. So in general, this is x minus 1 squared, x minus 2 squared, x minus 3 squared, and so on. And these kind of numbers actually appear in combinatorics. They are called central factorial numbers. So for our purpose, we want to express it in the following form, which is equivalent to these inequalities here. So whenever h is periodic, with no assumption on its average, then we have such an inequality here. Okay, so the coefficients are slightly more complicated, but let's just ignore them and concentrate on the integral. So this is basically the area, and this is basically the length. And this term is quite interesting. So if you recall, the curvature can be expressed as second derivative plus the function h. Then this term here can be regarded as the higher derivatives of the reciprocal of the curvature. So now the coefficients are not very important. So they are the coefficients of some polynomial. So as an application, we can make use of this inequality to obtain sharp lower and upper bounds for the isoperimetric deficit. That means lower and upper bounds for L squared minus 4 pi a. So with the same setting, assume that the curve is convex, and let's say rho is the reciprocal of the curvature, which is called the radius of curvature. So it turns out when m is odd, we can obtain a lower bound. So this involves this term here, which is related to the Ross inequality. So the Ross inequality says that this term here is always non-negative, and also some higher order derivatives of the curvature functions. And when m is even, so we have something similar, but it turns out we have an upper bound instead. Okay, so it seems to be rather complicated. So let's look at the case where m is small. So for example, m is 1, 2, or 3. So when m is 1, so we are in the odd case, and in this case all these terms just vanish. So this is just the isoperimetric deficit. L squared minus 4 pi a is non-negative, which is the isoperimetric inequality. And when m is 2, this is the Lin-Chies inequality for convex curve. So it tells you that the isoperimetric deficit is bound from above by the deficit of the Ross inequality. So a special case of the Ross inequality, or sometimes called the Heinz-Karcher inequality, tells you that the integral of 1 over k is always greater than or equal to 2 times the area whenever the curve is convex. So this one is always non-negative, and it turns out it can be regarded as a term which measures the asymmetry of the curve. So it can be regarded as an upper bound of the isoperimetric deficit. And then the case where m is 3 or higher seems to be new. So we can regard as a measure of the deficit of the Lin-Chies inequality. So what I mean is the following. So we know that the Lin-Child inequality tells you that if we subtract the deficit from the right hand side, then it's always non-negative. So we have this inequality. This is just Lin-Child inequality. But on the other hand, the higher order Wirtinger's inequality tells you that this deficit here can be measured by some higher order curvatures, namely the curvature of K, together with this isoperimetric deficit term. Okay, so this gives some measure of the stability of Lin-Child inequality. So I'll discuss the equality case in just a second. It turns out even for m equals to 2, the equality case can be long run, so it may not be a circle. So the idea of this higher order isoperimetric deficit inequality is simple. So we just make use of the higher order Wirtinger's inequality. So for the higher order Wirtinger's inequality, so this term here is the area, this term is the length, and this term is just some derivatives of the radius of curvature, which is h plus h double prime. So you can easily see this is just the k minus 1 derivative. And note that we have a minus 1 to the power m here, so the sign is changing depending on the parity of the integer m. So that explains why we have a lower bound when m is odd, and when m is even we have an upper bound. So it's also quite interesting to see that we actually have a long run equality case. That's because from the Fourier analysis we know that if the equality case holds, then the support function has to be of this form. So this equality here tells you that the curve, the convex curve, can be expressed like this. So it will consist of not just ei theta, so I'm using compressed notation, but also sometimes up to the e to the power I m plus 1 theta. For example, when m is 2, that means the Lin-Child inequality. So this one here. So even if the curve has some kind of oval shape like this, the equality can be sharp. Okay, so in this case, both the isoperimetric deficit and the Ross deficit are positive, but it turns out that they are equal. So we have some kind of funny shape here. So lastly, let me say something about the geometric meaning of the curvature terms or the higher order terms in the Wirtinger's inequalities or the higher order isoperimetric inequalities. So what I mean is the following. For the Wirtinger's inequalities, we have some terms which involves the higher derivatives of the support function like this. And correspondingly for the isoperimetric inequalities, we have some terms which involves the curvature on the curve integrated along C. So this is the some kind of higher order derivatives of the radius of curvature. For the simplest case where m is 2, so the smooth curvature of the radius of curvature is just itself, so integral of 1 over k. And in general, the integral along the circle of the k plus 1 derivative plus the k minus 1 derivative all squared can be split into two terms like this, so they look similar. And we can use integration by parts to obtain these two terms. Just apply integration by parts to the cross term in this expansion. So they are basically the same thing, except this one is of one order larger than this integral here. So geometrically, for example, when case 1 in this integral, then we know that the integral of h squared minus h prime squared is the area. I think it should be 2 times the area. And more generally, if k is greater than 1, then what does this term mean? So it turns out that this is also some kind of area. I think this should be actually 2. So this is also an area, but not for the original curve. So if we look at the convex curve, then we can define the so-called center of curvature like this. So for a fixed point x on the curve, we go inward along the normal direction by rho units, where rho is the radius of curvature. And this point here is called the center of curvature of that point. And as x varies, it will trace out a locus, which is called the locus of centers of curvatures. So this is obviously a closed curve. Okay, so for example, let us look at an animation. So this is a closed curve, the blue one, and the green one turns out to be the locus of the centers of the curvatures. And the red arrow here is just the normal vector scaled by the radius of curvature. So this is the locus of the centers of curvature. So if we take the algebraic area, meaning we look at the integral of x dy minus y dx along this locus, and then divide by 2, and that's called the algebraic area. So if we take the absolute value, then we got the total area. So it turns out we can directly compute the algebraic area, which can be expressed in terms of the support function h by this formula. And similarly, for this term here, which is of 1 order higher than this integral, this is in turn the area of the locus of curvature center of this locus of the curvature centers. So we have a family of loci of curvature centers. So these terms here, in some sense, measures the area of these loci of curvatures. So of course, if the shape is round, then the locus of curvature is just a single point which has area 0.